Okay. So thank you very much for invitation, and thanks for giving me an opportunity to talk here. Sorry about last minute change. I decided to talk about the brains and the representation instead of large duality or refined Chern-Simons theory. It's because one of the reasons is I really want to finish this paper during this day, just to put my pressure on to talk about this topic. So the goal of there are a few mathematicians and physicists, and so the goal of my talk is to show the relationship between the category A brane, so of the modular space of Lie connections of T2 mod point and SL2C, the modular space of Lie connections. With certain symplectic form, I will explain what it is, and the relation between representation of so-called double affine Hecke algebra of A1 type. So that's the goal of my talk. In the category A brane actually indeed contains the so-called Gaia category, whose object is usually the flat unitary bundle over the Lagrangian, but so I'm going to talk about the category which is bigger than the Gaia category. And so most of people are not familiar with the double affine Hecke algebra, so I would like to introduce what is double affine Hecke algebra. So this is the acronym of double affine Hecke algebra. So to introduce double affine Hecke algebra, so it's better, the most convenient to start with the so-called orbifold fundamental group of the T2 mod point over Z2. If you consider T2 point over Z2, so you consider the universal covering, and the point are the punctures, and there is the three generated. One is half tan T around the point, which identifies the opposite point. Sorry, I should mention that Z2 acts on the identifying the point opposite to the punctures. Okay, so therefore these 2 points are identified. So this stands for one generator of fundamental group, and I call this longitude Y, A cycle and B cycle. Let's see. So let's go X. Okay, so there are three generators, which is the X plus minus, Y plus minus, and T plus minus, and through the relations, so if you consider the T square X, Y, X inverse, Y inverse, which is 1, trivial, so therefore T square X, Y, X inverse, Y inverse, which is trivial. And also, you can consider the following generator, T, once you take T, so the arrow, the directional arrow is inversed. So T, X, which is also trivial. T, X is trivial. And also, if you look at the other generator, the other direction, T, Y inverse, Y inverse, which is also trivial. T, Y inverse is trivial. Okay. So this is the orbifold fundamental group of T2 mod point of mod point over Z. Okay. And double affine Hecke algebra is actually indeed you just deform the first relation by Q, and if you just deform the first relation by Q, introduce first deformation parameter, and also you add so double affine Hecke algebra, which I call H double dot, is indeed the Y inverse X inverse Y X T square is equal to Q, and also the other relation is just as it is, X inverse T Y inverse t is equal to y, and you have the quadratic relation, which is called Hecke algebra. T plus t inverse is equal to 0. So this is the double Hecke algebra. So this is small t. So please do not confuse. This is capital T, and this is small t, and the deformation parameter is small q and small t. These are two deformation parameters. And this is called Hecke algebra. Once Hecke algebra. Once you take t equal to 1 limit, this reduces capital T squared is equal to 1, so therefore it's just Y group, and Hecke algebra is a deformation. X and Y will give you affinization, and you have a two copy of affinization, that's why it's called double affine Hecke algebra. And the polynomial part satisfy this relation. And often, so people just relate, Q and T are C star variable, in deformation parameter. They are related by T is equal to Q to the C, where C is called central charge, usually. Charge. Okay. And also, as you can see, easily imagine from the construction, so the PSL to the action on a double affine Hecke algebra. So generator is the 1101, which I call it tau plus. Tau plus, x remains the same, and y is mapped to q to the minus 1 half xy, and also tau minus, which corresponds to 1011, which generates the PSL to z, is y stays the same, under tau minus y stays the same, x is mapped to q to the minus 1 half yx. And the sigma, so this is kind of T transformation. I don't want to use T transformation. The corresponding element for S, I call it sigma, so which is tau plus. So that is 1 minus 1, 0, 0. Tau minus tau plus, which map x goes to y inverse, and y goes to xt squared. So this is the PSL action, this action of the double Hecke algebra. There is an important sub algebra, so-called spherical sub algebra, which I denote H double dot. So which is inside H double dot. And I just introduced idempotent, which is T plus T inverse small t plus small t inverse. If you use a Hecke relation, this Hecke relation, one can show that the E square is equal to 1. So therefore it's called idempotent. And the spherical subalgebra is just you just sandwich by idempotent. Okay. Then, so what you would get is x is equal to x plus x inverse e y. So there's a 3 generator inverse e, and z is equal to this is y. So q 1/2 y inverse x plus q minus 1/2 x inverse y. So there are 3 generators, and which satisfy the following relations. So the x and y is q commutator will give you q inverse z, and it's everything cyclic relation. You just rotate x and y and z. And also you have qx square plus q inverse y square plus qz square minus q 1/2 xyz, which is equal to q to the 1/2 plus q to the minus 1/2 square plus q to the 1/2 t minus q to the minus 1/2 t inverse square. So this is the spherical subalgebra inside a double harmonic algebra. And so the definition of Q commutator is given by as follows: Q1 half AB minus Q minus 1 half BA. Okay. So this is the definition. Okay. And once you take, let's see, Q goes to one limit, everything, X and Y and Z, X, Y, Z becomes commutative. And what's left is here. Okay. As you can easily see, so the right-hand side is only depends on the formation of Q and T. So therefore, it commutes with even before going to Q equal to one limit. Since right-hand side only depends on deformation parameter, so this generator commutes with all the elements. So therefore, it's called center or Casimir. So it's called center of SH, spherical subalgebra. And once you take Q equal to one limit, so this commutator becomes trivial. So everything becomes commutative. What's left is here. And X square plus Y square plus Z square minus Q1 half XYZ is equal to Q1 half, 2 plus T square plus T minus square. Okay. So this, and in fact, this describes the moduli space of flat connections of T2 mod point or SL2C. Okay. So this inside a C3, you can just have a hyperplane defined by these cubic equations, which defines moduli space of flat connection. And what is the parameter? T is indeed, if you consider the torus with one puncture, you need to consider holonomy around the puncture, and the holonomy is indeed related by T minus 2, 0, 0. Holonomy of SL2C holonomy around the puncture is T square and T minus square. So therefore, this can be written in trace of B holonomy.
The Q disappears. Yeah.
Oh, sorry. Q disappears. Sorry. I'm sorry. So this is the relation. This is how the highs are related to modulus. So therefore, the spherical Daha can be understood as the spherical Daha can be understood as the quantization coordinate ring of the modular space of flat connection T2 mod point of SL2C, and there's in particular complex structure. I call it. I would like to call it J. I will explain what the meaning of J in later. In particular, so the holomorphic coordinate in terms of. Okay. And physically, so this X and Y and Z can be understood as the holonomy around the meridian. Meridian. X corresponds to meridian. Trace of X corresponds. So therefore, this is related to Wilson loop. Y is related to Hoof loop. Z is related to Dionic operator. So where this X square, Y square, Z square, this manifold, which is the modular space of flat connection, is indeed equal to the modular space of Coulomb branch modular space of the 4D n equal to 2 star theory on S1 cross R3. And Wilson-Hooft Dionic operator becomes a coordinate of the Coulomb branch of 4D n equal to 2 theory.
Is it a definition of Dionic operator?
The ionic operator is the this is in the meridian 1, 0, 0, 1, 1, cycle. So it carries both.
Generators of cycles, not the Wilson loop itself. Yeah,
So,
no gauge field, nothing. Yeah.
So this carries both electromagnetic charge. This means. Does the answer to your question?
I guess you get these line operators in the 4D gauge theory, right? But the description in terms of cycles is coming from constructing those line operators from like a 2, 0 picture.
Yeah.
Coming from compactification on the torus
Yes.
upstairs.
Yes. Sorry, I didn't get you.
But I mean that Wilson loop is just a gauge field, yeah, integrated somewhere. There is no gauge field in this description. You just describe contours.
Yes. Okay.
Sorry, Satoshi, so if you set q to 1, then the spherical data is just functions on that moduli space.
Yes.
One would hopefully expect the ordinary daha to be endomorphisms of some rank 2 bundle.
Yep.
Over that.
Yeah, that's true.
What bundle is it?
It's the what bundle it is? I know. I should know your answer. It's kind of a tautological bundle over the modular space of Higgs bundle. I can tell you later.
I guess that's an obvious guess, but
yeah.
Okay, just making sure.
Yeah.
Great.
Okay. Any other questions? Okay. I already erased, but I just want to understand the representation theory of this double affine algebra and the relation to the geometry of this modular space of Lie connections. So therefore, first I want to understand the representation theory of double affine algebra. Okay. So let's study about representation theory of spherical daha, not the daha itself. So to understand representation of spherical daha, you just consider polynomial representation and the morphism of polynomial CQT, actual Lingo symmetry functions. I think I should write the Z2. Where the CQT is the field of functions with respect to the variable q and t. It's a field of fraction of rho on polynomial q and t, and Z2 acts on the ordinary way, x goes to x inverse. Okay? So therefore, this is the ring of function is indeed the function with one variable, x plus x inverse. In particular, x is mapped to x plus x inverse. Okay, so this is y is mapped to some difference operator, tx minus t inverse x inverse t minus t inverse per bar pi. So this is a shift operator. I will explain. Minus t x inverse. Sorry, I told you wrong. So this is x inverse, x minus x inverse, and where this bar pi acts on the shift operator. If you shift operator acts on x, you just q. You get the multiplication by q. And the z is coming from, also the difference operator. However, so this, I'm not going to write the explicit form. You can just get from the computational relation.
I guess this answers Alexei's question that x is the value of the Wilson line. So like it's x plus x inverse, like e to the a minus e to the minus a, and then the loop line is the second one. Was that your?
I don't know if it answers because I think the question was that it's based on a conjectural duality that we didn't even explain.
Okay.
Yeah, I think it's okay.
Anyway, so this is called McDonald. difference operator. So that the indeed, so this ring of function has a basis. I call it P basis, which is called McDonald polynomial, which is called labeled by integer L. And as you most of the audience know, so the McDonald polynomial carries the so-called Young tableau, and SL2 case, rank 1 case, so it's only labeled by Young tableau with one row. And this number of boxes, I call it L. And so this actually becomes the basis of a ring of symmetric functions. And moreover, if the I call it polynomial representation. So this is called polynomial representation. It's called polynomial representation, and I call it PL. If PL of y hits on the polynomial, McDonald polynomial, and this becomes eigenfunction, and the eigenvalue is indeed q to the L t plus q to the minus L t inverse. PL. Okay. So this is the basis of, and this will give you uniquely determined McDonald polynomial. And furthermore, so one can study the representation theory of spherical Daha by just introducing so-called raising or lowering operator. P2. So you just increase the box of Young tableau by 1. P4 and so on. Okay. I call raising operator, lowering, raising, and the lowering operator. Where the raising operator is defined as x plus q to the L, q to the minus L, t to the minus 1, z, and the lowering operator is x plus q to the L, t to the z.
Indices also are 1, R2 on the diagram.
Okay, but that's fine. Okay. So once these operator acts under the polynomial representation on PL, in fact, you get some factor PL plus 1, and the polynomial representation acts on lowering operator. If acts on PL, you get some factor 1 minus q to L minus 1 t to the 4 over 1 minus q to the 2 L minus 1 t to the square P L minus 1. So therefore, raising operator increase the number of boxes, and lowering operator decrease the number of boxes by 1. Okay. And I'm interested in the finite dimensional representation, and to find a finite dimensional representation, it's better to look at some number, whatever, PL minus 1, lowering operator. If the lowering operator annihilates the McDonald polynomial, so then you can just consider the module CQT of x plus x inverse, the module generated by ideal generated by PL. So you can just kill all the right hand side and just take a quotient, and then you get the finite dimensional representation in this area.
Do the McDonald polynomials have a nice interpretation in 4D gauge theory?
I'm sorry?
If we translate things to 4D n equals 2 star theory, do the McDonald polynomials have some physical interpretation?
Good question.
They have interpretation in terms of 3D theory on the boundary, so they have vortex partition functions for certain values of the mass parameters.
Cool. And they diagonalize it with lines colliding with.
So that y operator is the eigenfunctions on the y operator.
Okay. So when this lowering operator acts on an annihilation operator is when this numerator vanishes. So therefore, one can consider the following cases. So when Q is 2L, sorry, I think we mix up a notation. 2n is equal to 1, and t square is equal to Q3 minus 2k minus 1, and the t square is equal to minus Q3 minus L. Okay. So I think I should follow the notation. I'm sorry, I just changed the mind. So I call it capital N and the small n. So in the first case is this first factor vanishes, and the second and third cases the second factor vanishes. Okay. So the reason why I pick the odd number is to avoid infinity in the denominator. So to avoid the denominator vanishes, I just need to pick the odd number in the exponent. Okay, and so you just put the minus sign in front in these third cases. So let's go to number 3. So in the case of number 1, so there is a Q is indeed e to the pi I over n, so root of unity. 2n of unity of 2n root of unity, and t generic. Okay, and t generic. In this case, you just consider so this term vanish when PL is equal to n. So therefore, I just define U of n, which is a finite dimensional representation, QT x plus x inverse over Pn. Pn, so this becomes finite dimensional representation. Moreover, so if you look at the shift operator defined here, the shift operator when acts on x to the n, x to the 2n, then it acts on q to the 2n, x to the 2n, which is trivial, which is just 1. I just impose q to the 2n is equal to 1. So therefore, it acts as a trivially. Okay. So therefore, one can also consider the following finite dimensional module, which is finite dimensional module, which is defined as delta. So I call it this is f to n. Substrict always means a dimensional module, finite dimensional representation. And since this is symmetric polynomial, and x to the 2n when the w, bar phi, so w acts on x to 2n, it acts on trivially. So therefore, if you look at the this Macdonald difference operator, so the Macdonald difference operator acts on this polynomial trivially. Okay. So you can just act on trivially. So therefore, ideal generated by this polynomial is invariant under the action of Frege-Dach. So this delta is actually indeed just the ordinary, the complex parameter. So therefore, this finite dimensional representation is parameterized this free parameter C.
And what does the raising operator do to Pn?
To the Pn.
Yes.
Raising operator
Yeah.
to the Pn.
Yeah.
you just give you Pn plus 1.
No, I understand that then. And why it terminates?
It terminates.
Yeah. Why it is finite dimensional? So why don't you get arbitrary degree?
Because lowering operator kills.
Lowering, yes, but
yeah.
Raising
does not kill. So therefore, this ideal generated by Pn.
So it consists of small degree, of low degree polynomials, yeah?
The ideal consists of all the higher degree.
Higher degree, yeah.
And then the quotient by that ideal is finite dimensional.
Okay.
Is it okay? Okay. So therefore, so in the case of 1, so you have two finite dimensional representation. And in particular, so when delta is equal to 2, so the p to the n is indeed x to the n plus x to the minus n. So therefore, when delta is equal to 2, this polynomial is indeed, so when delta is equal to 2, x to the 2n plus x to the minus 2n plus delta is equal to Pn square. Pn square. So therefore, this finite dimensional module is split into two parts. Delta equal to 2 is split into un is equal to 0 and zeta y. Un is where zeta y is indeed the sign flip of y eigenvalue. Okay. So therefore, and the second case is when t squared is equal to q to the minus 2k minus 1. And so therefore, I call the central charge is minus odd number over 2. Remember that the central charge is defined by relation between t and q. So in this case, polynomial representation acts on 2k annihilates the McDonald polynomial. So therefore, you can define 2k as the quotient of ideal ring of symmetric function divided by P2k. So this P2k, and this 2k dimension is split into two parts. D2k is equal to dk plus dk minus, where the dk plus and dk minus are related by the sign flip of x and minus x. Yes. For instance, so when k equal to 1, let's see, k equal to 1, P2k, let's see, so this is generated by 1 plus 1 and, sorry, you cannot see this part. I think it's, so when k equal to 1, so this finite dimensional representation is generated by 1 and P1, which is x plus x inverse. So the dk plus is indeed, I call it small x. It is generated by CQT 1 plus x, and dk minus is generated by 1 minus x. And they are related by sign flip, x and minus x. Okay. And the third case is I call it is t squared minus is equal to minus q to the minus n. So this is there are only one finite dimensional representation, which is I call it Bn plus 1, and C QT x plus x inverse divided by p n plus 1. So there's only one finite dimensional representation, which kills the second factor. And one can consider the hybrid cases. So for instance, the hybrid case. For instance, when the both 1 and 2 are satisfied, 1 and 2 are satisfied, so in this case, you have both the, let's see, so there are 3 finite dimensional representation, U and F and the D. Okay. So in this case, you can have a short exact sequence. Un goes to dk plus dk minus goes to 0. And in fact, you have the n plus 1 goes to 0. So this V show up when you take the quotient between B, where the, sorry, I think I should mention that the n is equal to n plus 1 minus plus 2k. So there is a relation between capital N, small n, k. When they are related to each other, you have a short exact sequence. Okay. So therefore, once you impose 1 and 2 condition, you immediately get the number 3.
Should you fix delta in this case?
Delta?
You have this parameter delta in the case 1, yeah?
This one?
Yeah.
This one doesn't show. Does not show up in this case. So I just use this un. So here un.
So this exact sequence is true for all deltas or only for delta equal 2?
But this exact sequence does not involve this f. Only f involves delta. Okay. So these are finite dimensional representation coming from the both polynomial representations. And I just want to understand these finite dimensional representation in terms of geometry, Hitch modular space. So therefore, I just want to study first geometry of modular space of black connections. T2 mod point over SL2C. So modular space of black connections of T2 mod point over SL2C is equivalent to the modular space of Higgs bundle, so-called, of T2 mod point of SU2, which is defined by you just consider a pair of the holomorphic bundle with the so-called Higgs field. So E is a rank 2 holomorphic vector bundle over T2. And the phi is the holomorphic section of T2 mod endomorphism of E times canonical C. So the holomorphic section. And you just consider the stability condition, which is called the Hitch equation. You consider the following equation. That will give you the stability on the modular Higgs bundle. And furthermore, so you have to specify the meaning of punctures. In the puncture, you just identify around the puncture, you just put the ramification data. So the gauge connection of the bundle is alpha p d theta plus dot dot dot, and the phi is equal to 1/2 beta p plus gamma p dz and over z. So where I just put the coordinate of puncture, and I call this the angular direction is theta, and z is the local coordinate around the punctures. And alpha p and beta p and gamma p takes the Cartan sub algebra of the gauge group T. And in fact, so this Hitching equation is equivalent to the, you just put the phi plus phi bar times I is, you just define this complex connection by the connection plus Higgs field, and this is equivalent to the flatness condition AC which AC equal to 0. Okay. So therefore, the modular space of flat connection is equivalent to the diffeomorphic to the modulus of Higgs bundle, which is called non-abelian Hodge correspondence. Hodge correspondence. Okay. And these modular spaces are hyperkähler manifold, so therefore it carries three complex structures which satisfy Courtonian algebra, and I take I as a complex structure coming from Riemann surface T2 mod point, and a J coming from SL2C group, SL2C group, or people call character variety. So therefore, I already erased the equation for modular space of flat connections. So the modular space of flat connection is defined as a cubic equation, 2 plus trace B, and this x, y, z coordinate are holomorphic with respect to complex structure J. Okay. So therefore, what we have seen in the Sverga-Daha is the deformation quantization holomorphic coordinate with respect to complex structure J. Any questions so far? Okay. And I just want to mention, so here trace B is actually indeed t squared plus t minus square. Okay. And this t is related to this ramification data, and t is indeed related by exponential I times gamma p plus I alpha p. Sorry, strictly speaking, this is b. T squared, t minus squared, 0, 0. Times 2 pi. So therefore, the ramification data with alpha and gamma is related by holonomy of SL2C at the puncture. Furthermore, so you can define the corresponding Kähler form, symplectic form, omega j and omega k, and you can define the holomorphic symplectic form in the following, just combination of the symplectic form, like this way, omega k plus everything cyclic. I omega homomorphic omega k is omega I plus I omega j, And this omega j can be written in terms of this holomorphic coordinate, dx wedge dy mod 2z minus xy. So this is holomorphic coordinate. And I just want to understand the geometry of modular space. And this geometry of modular space is indeed becomes clear when you take this ramification bounding. It becomes nilpotent indeed. So that when t equal to 1 case, it's equivalent to there's no puncture on the torus, two torus. In that case, the modular space of Lie connections of T2 mod SL2C, sorry, T2 of SL2C is C star cross C star mod Z2. Where this C star is indeed, is the, if you just consider meridian longitude, so meridian holonomy is, and the longitude holonomy is takes x and x inverse, y and y inverse. X C star is spanned by one of the eigenvalue. The other C star is the other eigenvalue, and Z2 acts a residual Y group. And if you can consider the real locus, so which is SU2, which is S1 cross S1 mod Z2. If you consider the compact group, subgroup in SL2C, so you just consider the real subgroup. So this is indeed the T2 mod Z2. So therefore, it's called a pillowcase. So this will give you lots of information about how the geometry look like. And so what's nice about this non-abelian Hodge correspondence, you can use the Hitchin fibration furthermore to understand the geometry. The Hitchin fibration is this modulus the Higgs bundle to the trace of affine space, which is defined by trace of phi squared. So this map, Hitchin map, is the complete. In some sense, the complete integrable system. So therefore, if you consider generic point, so you have a complex tora. In this case, generic fiber is just topologically T2. However, if you look at the preimage of 0, which is called global nilpotent cone, global nilpotent cone has this real locus of the modular space flat bundle. When t equal to 1, so this global nilpotent cone indeed is equal to this real locus, and I just want to call it Ban G for some reason. And so this, when t equal to 1 case, it's just the global nilpotent cone is the pillowcase. So I call it Ban G. So the pillowcase, the reason, so I think you have a torus and you have a Z2 action, just identify the opposite point, and the fundamental region is here, so you have a fourth singularity. So which I just write down these 4 points. Once you turn on the T parameter, so this fourth singularity is smooth, becomes smooth. And the other compact divisor will appear. So these are the topologically S2, and so S2. And since this is elliptic fibrations, and singular fiber is classified Kodaira, and it's called, and for that classification it's type 1 tilde star. Okay, I think it's U. Yes, sorry. And since this singularity looks like a affine D4 thinking diagram, it's also called the affine D4 singularity. And also, so this using this the Hitchin map, one can say that the generic fiber of this Hitchin fibration are homomorphic in complexure I, and however it's Lagrangian, so it's an integrable system, so that the generic fiber are Lagrangian with respect to the other complex structure. So in the physics language, a holomorphic submanifold is B brane, and the Lagrangian submanifold is A brane. So therefore, physicists call BAA brane. So one can ask a similar question: what about this irreducible component in global nilpotent cone? That in fact, sorry, I just want to tie my shoe. One can say that so if I call it D1, D2, D3, so D4. So these are these divisors show up once you turn on the T parameter. So therefore, it's called exceptional divisor. And once so D1 omega I evaluated to D1 is indeed alpha, the parameter alpha, and the omega J evaluated the exceptional divisor is indeed the parameter beta P, and gamma P show up when you evaluate omega K in the exceptional divisor. There is a symmetry between exceptional divisor, which just map x goes to minus x, y goes to minus y. So remember that so this direction is meridian in the torus, this direction is longitude in the torus. So therefore, so once you swap the sign of meridian and longitude coordinate, so this external divisor are swapped. So therefore, there is symmetry. So if you replace D1 divisor, the other divisor, the parameter match should be just equivalent. So therefore, as you can easily see from this relation, external divisor, once you turn on the holonomy around the puncture, this external divisor is no longer holomorphic. I mean, in general, no longer holomorphic in complexure I and the Lagrangian J and K. Okay, so therefore, so the external divisor sees the omega J and omega K once you turn on the holonomy. So therefore, I mean, Hitchin map tells you that these external divisors are Lagrangian. However, they are no longer BA type in general for once you turn on the holonomy. And I have to tell you one more thing. So this compact divisor is indeed generates the second homology of the modular space of Higgs bundle of Z is generated by this divisor Di and Van G. So they are generator of the second homology group. And as you can see, T2, generic fiber is also T2. So therefore, its element in H2. And in fact, this I call it capital F, bold F. Generic fiber can be expressed as Van G times 2 and union sum of di. Okay. So in the second homology, the relation between Bungie and the exception divisor and the generic fibers. So this I call a fiber cross relation. Okay. So with this preparation, one can compare between the representation and the geometry of modular space of flat connections. And to connect the representation and the geometry, I use the brane quantization. So this is due to Cook-Witten. I just consider to go to the brane quantization. You just consider 4 equal and 2 star theory. On the S1 cross R cross R2Q, you just consider I didn't mention at that time, but this parameter omega deformation Q will introduce the deformation parameter in spherical Daha, and you just compactify on T2. So the way you compactify is as follows. So you just consider S1 cross R times, you consider R2, and you just introduce omega background Q. And so the way you compactify is you just compile this S1, and also you just compactify along the axis omega deformation. So this S1 times, I call it S1Q. So this will form T2. Then if you just compactify it, you just get the strip, and the boundary is indeed the axis of omega deformation. And what you would get is 2D sigma model, and whose strip is, I call it, I didn't introduce sigma. I call it sigma. Sigma is mapped to the modular space of Coulomb branch, which is modular space for flat connection T2 mod point over SL2C. Once you compactify on this sigma model, you have some half plane and with boundary, and you have to impose some boundary condition. And I'm interested in the A model. So I just want to consider A model, the boundary condition in A model. In fact, so the boundary condition we want to impose here is a special one, and since usual A-brane are flat unitary connection bundle over Lagrangian. And when you say Lagrangian, you have to specify symplectic form. So I'm interested in the sigma model and the A model with respect to omega x. And the omega x is indeed is imaginary part of, you just introduce I times, you just scale holomorphic symplectic form with respect to J, and you just scale I over H bar. Where the H bar is the some complex parameter, and if you write down h bar is capital the absolute value times e to the I theta. This is indeed equal to minus 1 h bar omega I plus sine theta plus omega k cosine theta. So this is a simplex form I'm interested in. So usual Lagrangian is usual A-brane is the flat unitary bundle over Lagrangian with respect to this omega x. So I call it BL, Lagrangian L, which is flat unitary bundle over Lagrangian. And usually, so you have C1, this S bundle is curvature, and the flat means FL is equal to 0. But you can also introduce in sigma model B field. So I call it FL plus B equal to 0. So this is a usual A-brane. However, so I don't want to use this part. However, Kapustin oral show that the some A-branes are supported on isotropic submanifold. Kawasaki submanifold is the submanifold locally defined by Poisson commuting functions. And Poisson function coming from omega x. So therefore, so the maximum number of Poisson commuting function, the half of dimension target space. I'm sorry, I think I break the mic. I hope it's okay. Yeah. So the maximum number of Poisson commuting function is a half of dimension target space. In this case, the modulus with flat connection. However, so the number of Poisson commuting can be less. In that case, the dimension of isotropic submanifold can be half of dimension target space. And there is one distinguished object called canonical, called isotropic brane, who supports target space itself, moduli space of flat connection of T2. I'm not going to write everything. And you just consider the target space itself, and you consider rank 1 line bundle whose curvature satisfy the following conditions. Curvature plus holomorphic, I think plus B field satisfy J plus omega x. So this is the A-brane, big A-brane. Big means bigger than the Lagrangian support. So this behaves like an A-brane. And moreover, if you consider BCC, so I call it BCC, canonical coseric brane. Moreover, if you consider the string between two boundary conditions, in mathematical language, the morphism between BCC, this will give you the space of holomorphic functions with respect to omega x f plus b inverse, which is j. And what we learned is that the space of homomorphic function on the target space is indeed the spherical Daha. And its Q parameter in the spherical Daha is related by e to the 2 pi I h bar, which introduce the in front of the homomorphic symplectic form here. So therefore, the boundary condition we want to impose that come from the reduction from for the n equal to 2 star theory on 2 sigma model is indeed BCC. And in fact, if you consider, as I mentioned, the line operator will give you the coordinate of the modular space of Clark connections. And if you turn on the omega background, so then you just wrap the line operator on this S1 direction. And if you turn on the omega deformation, everything's localized in this axis omega deformation. And in fact, so this algebra line operator will give you spherical Daha, and even if you reduce on a T2, the algebra line operator or spherical Daha appears from the axis omega deformation. So therefore, this picture will connect for the n equal to 2 star theory to the sigma model. Okay. The question is how you connect the representation theory and the geometry of the modular space Clark length as follows. You just consider another strip, which is, so you just first you consider BCC, and you also consider another strip, BCC, BL, which has a Lagrangian support. You just consider joining of the boundary condition will give you another BCC BL string. So therefore,
you can just consider local operators on BCC as an algebra acting on that Hilbert space, if you like.
What do you mean local operator on the BCC?
Yeah. Oh no, sorry. So in the picture on the right, you can use a state operator correspondence and turn. Right, the strip on the left is describing local operators sitting on BCC.
Okay, local operator.
Sorry, never mind. Never mind. Go on.
Okay. Okay. So therefore, homo BCC can act on the space of homo BCC BL. BL. So by joining the middle boundary condition, you get another BCC BL. And we know that this is spherical Daha, and you get the representation associated to Lagrangian support. Okay. So therefore, this is the module of spherical Daha. This picture will give you the first conjecture. You have a brane of flat connections of omega x and the representation category of spherical Daha of rank 1. And then, so left hand side contains more than Lagrangian support, so which has not been defined yet, but we expect there is some whatever R home equivalence between two categories. So on the one hand, you already saw the finite dimension. We have seen the finite dimension spherical Daha. There must be corresponding Lagrangian brane in the left hand side. Okay, that's what we want to identify. in the left 20 minutes. So to identify the Lagrangian brane for finite dimensional representation, it's very useful to consider the following formula. The dimension of this representation will come from Grothendieck, whatever. I think this itself, I think it's a Hirzberg-Riemann law, BCC, and wedge Chern of BL inverse, wedge tot of L. So I think Grothendieck Hirzberg-Riemann law formula. So therefore, once you have the compact support of compact Lagrangian support, so this formula will give you finite answer. This formula will give you finite dimensional integral. So therefore, so if you have a finite dimensional representation, so you have a compact A-brane with compact Lagrangian support.
Are you secretly using some correspondence with B-branes?
Yes. I think this formula comes from the near symmetry. And the point is,
sorry. I was going to say mirror symmetry or hyperkähler rotation, but maybe you'll tell me they're the same.
It's actually neither one. It's just looking at this BA branes, where they're B branes. That's all.
Yeah, great. So it's just looking at them in a different complex structure.
Exactly.
Great.
First, you can just look at the and if, fortunately, so this Fitching vibration will give you the compact Lagrangian brane. So as we have seen, so these generic fiber are the Lagrangian. In particular, this is BAA brane, and which is compact. So therefore, you can easily imagine this will give you one candidate for finite dimensional representation. So the F is always of BA brane. And if you look at did I erase the formula for omega x? Okay. Omega x. So this, the A brane, the brane supported on generic fiber can be Lagrangian only when theta is equal to 0. Okay. The other parameter, this is a mixture of omega I and omega k. Okay. So the simplex form is a mixture of omega I and omega k. So you have to kill the contribution of omega I in order for this brane to be Lagrangian. So therefore, in order for the brane supporting generic fiber to be Lagrangian, omega x has to be theta equal to 0, which means the 1 over h bar absolute value omega k. So therefore, h bar has to be real. What I meant is, okay, so I should mention theta equals 0. Okay. Theta has to be 0.
Pi maybe.
Huh? Or 2 pi times integer. 2 pi times integer. And in that case, you can just easily evaluate the dimension, and the f plus b is equal to minus omega I over h bar. H bar. And if you use this Grothendieck-Riemann log formula, dimension b, L is equal to f, it will give you 1 over h bar. And since this Grothendieck-Hirzberg-Riemann formula has to give you integer. Okay. So h bar has to be also quantized. So this has to be integer. So therefore, so if you look at the q is related to e to the 2 pi I, So this will give you Q has to be root of unity. And if you use this fiber cross relation, in fact, this is indeed, it has to be 2z, even number. So therefore, it's 2nth root of unity. Now we already seen. So this is equal to 2n. So we already see such a representation. So I call it this. We call it f to n delta. So this corresponds to representation f to n dimensional delta. And as we have seen, this delta has a free parameter, and so this brane can have the actually holonomy because the support is T2. So this free parameter can be identified with the holonomies. Okay. So what about the other representations? And as you can imagine that there is another compact Lagrangians coming from the global unipotent cone. And so you can just look at when these irreducible components inside the global unipotent cone become Lagrangians. And for instance, let's look at the exceptional divisor. di. So this di is only Lagrangian, becomes Lagrangian when alpha p plus I gamma p is equal to I h bar. So when this ramification data satisfied this condition, it's Lagrangian with respect to omega x. So in fact, in this case, so you can just put, and also we just seen that the t square exponential or 2 pi alpha plus I gamma. So there, the t in the spherical dipole is related by alpha and gamma by putting an exponential. And if you use this relation, one can conclude that the t is equal to q to the some real number. Some real number has to be some real number. If you just use these two relations, t has to be some real number. Furthermore, if you compute this Grothendieck-Riemann-Loeb formula for exceptional divisor, what you would get is as follows. So this is equal to alpha plus I gamma over h bar. The alpha plus I gamma minus 1/2 is equal to. So this dimension can be written. So this is in fact central charge C. So remember, t is equal to q to the c, which is equal to e to the 2 pi I h bar c. And we identify t and the alpha plus I h bar, I h gamma by this formula. So this has to be integer. So this condition is equivalent to t is equal to q to the minus 2k minus 1 over 2. And in this condition, what we've thought is that there's a finite dimensional representation coming from finite dimensional representation when this condition is satisfied. So therefore, that's why I call it dk plus and dk minus. And as we saw before, this corresponds to f to n delta. And they are related by dk plus dk minus are related by sign reflection x goes to minus x. And that what we saw in the finite dimensional representation, x goes to minus x. And furthermore, if you take y reflection, y goes to minus y, you obtain the corresponding finite dimensional representation. Sorry, y dk minus. Okay. So likewise, you can see the corresponding finite dimensional representation for band G by looking at when band G becomes Lagrangian. So this band G becomes Lagrangian only when minus 2 gamma p plus I 1/2 minus alpha p over I h bar is real. And if you compute the dimension of the B band G, so this will give you 2c minus 1 over 2h bar minus 1, and which has to be integral. And this condition will give you t square is equal to minus q to the minus n. So in this case, what you get is finite dimensional representation of B n plus 1. So therefore, I call it this is case 3. So this is indeed case 1 in the and the case 2. And this is case 3 in the beginning of talk. So therefore, this band G corresponds to B n plus 1. And this B is indeed called non-symmetric Fehling algebra. So B comes from Fehling algebra. So the quantization of band G will give you the Fehling algebra. And the algebra structure cannot be seen. Algebra structure only when you consider base manifold 3-point spheres, 3-puncture sphere. But in this case, we just look at the one-puncture torus. So therefore, we cannot see the algebra structure. But in any case, from band G, you get the quantization of band G. Okay, so these are the correspondence between finite dimensional representation and the compact A-brane with compact support. And I just want to, to wrap up, I just want to mention what does the short exact sequence mean in the language of geometry. So what we have seen as follows. So there is short exact sequence, delta is equal to 2 to n is un goes to 0, un zy. So what we have seen is this short exact sequence, and also we have seen this short exact sequence dk plus dk minus goes to 0. And here you have a Fehling algebra n plus 1. So in this short exact sequence, what you can see is that it follows. We identify this F as the brane supported on generic fibers. When delta equal 2 is when the holonomy vanishes. So in that case, this generic fiber can hit on the global nipotent cone, and indeed it splits in two parts. Maybe I should use different colors. So it splits to this part and also the other part. And they satisfy perfect cross relation. So band G plus 2 exception divisor plus band G plus the other exception divisor is equal to F. So this satisfies fiber class relation, and this brane has to be the Lagrangian. So you have to impose the condition when gamma p equal to 0. When you impose gamma p equals 0, these bound state of brane, this red part becomes also Lagrangian. So therefore, this short exact sequence is that when this generic fiber, the brane supporting generic fiber hits on global uniform cone, and it splits into two parts. Likewise, the second short exact sequence as follows. So we already identify UN is one copy of this red part. One copy of red part, which consists of Bungie and the two excitation divisor. And once the quantization condition and when the brane DI excitation divisor and Bungie exist, is indeed both you just impose the condition for case 1 and the case 2. If you impose two conditions, the existence of case 3 is immediately follows. And so this red brane is split into the irreducible component, Bungie and the excitation divisor. That's the meaning of short exact sequence. So therefore, the bound state operates. So that's the meaning of short exact sequence. And so we can see the one-to-one correspondence between finite dimensional representation of the spherical Daha and the compact Lagrangian brane in the modulus of Flack connection. That's the one evidence between relationship between these two categories. Thank you very much.
More questions?
Can you use this to get representations of actual Daha, not the spherical?
So the so Oblomkov showed that this representation Daha is equivalent to rep of Daha, and in fact you just consider so the S1 cross R cross Q R2. This is the for the n equal 2 star leaves, n equal 2 star leaves, and you put the surface operator of Gukov-Witten type in here. So this is the Gukov-Witten type defect, the surface operator. Okay. And you just consider the line operator on the surface operator. That will give you the actual double Hecke algebra. And the Morita equivalence can be understood as follows. You consider ordinary BCC, which will give you spherical Daha, and I call it BCC coming from the line operator on the surface operator. So and you just consider the strip in between. So therefore, if you have a BCC, BL, this will give you module, and if you just combine them together, you get the BCC check hat with BL. So Daha module come from spherical Daha module, and vice versa. If you swap if you change the strings between BCC hat and BC, you get the Morita equivalence in between. And this is indeed actually related to module EHW dot. So there is a one-to-one correspondence, this strip and the EHW dot.
So that thing is just the bimodule that misses the Morita equivalence.
Yeah.
It's not obvious these are Morita equivalent.
It's obvious to what?
It's not. I don't think it's obvious that these are Morita equivalent. It has to do with some property of this tautological bundle. I think that you're saying endomorphisms of this bundle are matrix algebra over just functions in space.
Yes.
Which is nice. So
okay.
Yeah, and then you get everything.
If not, let's Satoshi again.